Hello students, in this video we have assignment 6.4 and 6 questions but very easy. Very first one is 4 units of self-inductance and then dimensional formula which I will skip. You can find out by yourself. We'll see definition of 1 Henry, what is Henry, and then we'll see definition of 1 Henry. These two are related and very important questions, energy and energy density of an inductor. And in between, we have one more formula for self-inductance, which we'll see that if I change coil or number of turns of coil or dimensions of coil, how L gets affected. Okay, so that is the assignment. Let us start with the assignment. In the previous video, we saw that self-inductance can be expressed in terms of flux as total flux linked with the coil per unit current passing through it. That is one definition, and from this definition itself, we get 1 unit of self-inductance, that is Weber per ampere. What is Weber? Unit of flux. Ampere is unit of current. So this is 1 unit. Second equation which we had was self-inductance is induced EMF per unit rate of change in current. So taking dt on upper side in numerator, we have another unit volt second per ampere. So that is second unit. And then we know that from Ohm's law V by I is resistance. So I can also write this as ohm second. Okay, so these are the 3 units of self-inductance, but none of these are conventionally used, though not wrong, but not very much popular units. Popularly, self-induced EMF or self-inductance of a coil is measured in terms of Henry, denoted by H, symbol is H. How do we define 1 Henry? 1 Henry, you will get this answer to be 1 when you have 1 volt of self-induced EMF produced corresponding to 1 ampere change every second. So when rate of change in current is 1 ampere per second, and if you see that 1 volt is the induced EMF, then the self-inductance is said to be 1 Henry. So that is the definition of 1 Henry. Now coming to important point, that is the energy stored in the inductor. So we know that the self-induced EMF can be given as epsilon is equal to L di by dt, and we also know that power, electrical power, can be given as voltage into current. So can I write power as rate of change in work, rate of doing work? Then the equation becomes this. Rearranging the terms, we get dW to be L I di by dt. Sorry, dt won't be there. Simply L di. And we know that dW, that is work is energy. So du, whatever work we do is stored in terms of potential energy. So dW can be written as du, that is change in potential energy, and then this is what we have. Integrating both sides, we get IDI. You can take limit of integration, or else we may take it from 0 to I, and then we have U is equal to half Li square. So this is the expression for potential energy of the inductor, energy stored inside the inductor. Now there is one quantity called energy density. What do you mean by energy density? Energy density is how much energy you are storing per unit volume. It is denoted by rho. So rho is energy stored per unit volume. So in case of inductor, it is denoted by rho B. So if I express rho B, it is U upon volume. Okay, how much is the energy? It is half Li square. And how much is the volume? Area into length of the coil. And then I have rho B is equal to half Li square upon Al. Now we keep this equation aside and we'll come back to it later. First, we have to derive one expression for L. We know that L can also be written as total flux per unit current. And how do we express total flux? It is NBA. Okay. And what is B? B is mu 0 Ni. Okay, magnetic field of the coil is mu 0 Ni. So L is mu 0 N N A. What is N? Total number of turns. What is N? Number of turns per unit length, and A is area of cross section. So I can say that L is mu 0 N by L into A. Don't get confused between these two L. This is self inductance, this is length of the coil. Okay, so L is mu 0 N square A by L. This is the expression of self-inductance in terms of physical parameters. We should be knowing that if we change medium of the coil, that is mu 0, how L is affected. We should be knowing that if we change number of turns of the coil, how L is affected. We should be knowing that area directly affects L. And if we change length of the coil, self-inductance decreases. One thing I would like to highlight here is that L has nothing to do with current you are passing through it, but self-inductance is sensitive to length of the coil. If you double the length, self-inductance will be half. If you half the length, self-inductance will be double. But that is not true with number of turns. If you double the number of turns, you are making self-inductance 4 times. If you half the number of turns, self-inductance will be reduced by 4 times. Okay, and we have direct proportionality of area of the coil and self-inductance. So now if I label this as equation 3, let us use 3 in 2. So what do I have? Rho B is half I square by AL, and instead of capital L, I use this mu 0 N square A by L, mu 0, sorry, capital N should be N square A by L. And then what do I have? Half mu 0 N square. Now see, this A and A gets cancelled out, and I take it as L square. Capital L square by L square gives me small n. Okay, and then I am left with I square. So if I multiply and divide with mu 0, what do I get? I have mu 0 square N square I square by mu 0 1 half as it was. Why to do this? Because we know that mu 0 Ni is B, and then we have rho B as B square by 2 mu 0. This is the expression for energy density of an inductor, which says that mu 0 is constant, 2 is constant, and hence the energy density of coil is in terms of magnetic field. So Inductor stores its energy in form of magnetic field. If you remember, we had earlier one equation, rho E is half epsilon 0 E square. Which expression this is? This is the expression for energy density of capacitor. So capacitor stores its energy in form of electric field, inductor stores energy in form of magnetic field. So that is the assignment, and that is all for now. Thank you.